Kumar Singh, and I am going to present uh, mm, my uh, paper on design of 4.8 to FFT structure on Xilinx, and I am doing my MTech from IIT Kurukshetra, and basically I just want to tell you that FFT and IFT structures are very critical in the field of digital signal processing, and these days we are implementing these structures on FPGA kit for the better performance, high speed. So we are actually using application specific integrated chip for this for the high performance, and butterfly structure is the basic unit of FFT and IFT implementation. So, and each butterfly consists of different multipliers, adders, and so in my structure I have implemented 4.8 FFT structure that contains the adder like cobblestone adder and ripper carry adder with the multiplier like booth multiplier. Okay, so I have used JDX4 booth multiplier in my implementation. So what I have done is to main my motto is to reduce the delay. So what I have done is we have used cobblestone adder, that is the known as the fastest adder, and that is known as the fastest adder with the least delay. And these days what we are observing these days is we are actually compromising chip area for the delay. So this is the basic thing, and I am using Verilog programming language to design it and implement it on Xilinx IC Design Suite 14.7 platform. So this is the basic concept what I am doing in the introduction part. So what actually it means, I am going to tell you in detail. So actually we have any signal that contains the different frequency component, and in time domain it is not visible. So we need some particular structure that will convert those time domain signal into frequency domain signal, so that we can get to know that what frequency component is present in that time domain signal, so that when we get the frequency component of some random signal, we can see that some of the noises are present in that random signal. So we can design a filter also, so to reduce, to eliminate that particular noise. So it is very important to know the frequency component, different frequency component present in a random signal, because and so that we can analyze it, and we can design filters in the further processing. So it is very important to find out the frequency component in the noise also, because these days every signal is mixed up with so many frequency component. As Fourier says that we have a signal that is that can be, every signal can be represented in different frequency component of sine and cosine. So this is the basic concept behind the evaluation of FFT structure. So why FFT? Because the FFT is nothing like a new thing that is happening. Basically, FFT is the way to compute DFT in the quicker way. Means we are computing DFT in the fastest way possible. So what we are doing is we are just here you can see this is the first XM is the first one is the here you can see here that it is the DFT equation, and we split this DFT equation into two parts, and we are splitting again and again until we get the lowest level. So how this is how FFT structure actually faster than DFT structure. So and because we are splitting that particular equation in again and again and again. So we have, if we have n samples, so in that case in DFT calculation we required n square operations, but FFT is doing tremendous job by reducing it up to n log 2n. So this is the trick. Okay, so trick here is to speed up DFT by taking advantage of periodic nature of sinusoid. So we have sinusoids that has a period, so DFT is taking advantage of that particular thing. So we can first divide up the DFT into even index summation, where the subscript for even index sample is 2m and odd index sample is 2m plus 1. Now we have DFT as the sum of two smaller summations and each half of the size of the original. we can split this process and each of these even and odd index summations into their own even and odd index summation. So we are actually using